Chapter 4. Data Structures, Objects and Arrays. On 2 occasions I have been asked, "Pray Mr. Babbage, if you put into the machine wrong figures, will the right answers come out?" I am not able rightly to apprehend the kind of confusion of ideas that could provoke such a question. Charles Babbage, Passages from the Life of a Philosopher. Numbers, booleans, and strings are the atoms for which data structures are built. Many types of information require more than one atom, though. Objects allow us to group values, including other objects, to build more complex structures. The programs we have built so far have been limited to the fact that they were operating only on simple data types. After learning the basics of data structures in this chapter, you'll know enough to start writing useful programs. The chapter will work through a more or less realistic programming example, introducing concepts as they apply to the problem at hand. The example code will often build on functions and bindings introduced earlier in the book. The weresquirrel. Every now and then, between 8 p.m. and 10 p.m., Jacques finds himself transformed into a small furry rodent with a bushy tail. On one hand, Jacques is quite glad that he doesn't have classic lycanthropy. Turning into a squirrel does cause fewer problems than turning into a wolf. Instead of having to worry about accidentally eating the neighbor, that would be awkward, he worries about being eaten by the neighbor's cat. After 2 occasions of waking up on a precariously thin branch in the crown of an oak, naked and disoriented, he has taken to locking the doors and windows of his room at night and putting a few walnuts on the door to keep himself busy. But Jacques would prefer to rid his condition entirely. The irregular occurrences of transformation make him suspect they might be triggered by something. For a while he believed it happened only on days when he had been near oak trees. However, avoiding oak trees did not solve the problem. Switching to a more scientific approach, Jacques started keeping a daily log of everything he does on a given day, and whether he changed form. With this data he hopes to narrow down the conditions that trigger the transformations. The first thing he needs is a data structure to store this information. Datasets. To work with a chunk of digital data, we first have to find a way to represent it in our machine's memory. Say for example that we want to represent a collection of numbers 2, 3, 5, 7, and 11. We could get creative with strings after all. Strings can have any length, so we can put a lot of data into them and use 2, 3, 5, 7, 11 as our representation. But this is awkward. We'd have to somehow extract the digits and convert them back to numbers to access them. Fortunately, JavaScript provides a data type specifically for storing sequences of values. It's called an array and is written as a list of values between square brackets separated by commas. The notation for getting at the elements inside an array also uses square brackets. A pair of square brackets immediately after an expression, with another expression inside them, will look up the element on the left-hand expression that corresponds to the index given by the expression in the brackets. The first index has an array of 0, not 1, so the first element is retrieved with list of numbers 0. Zero-based counting has a long tradition in technology and in certain ways makes a lot of sense, but it takes some getting used to. Think of the array as the number of items to skip counting from the start of the array. Properties. We've seen a few expressions like myString.length to get the length of a string and math.max, the maximum function, in past chapters. These expressions access a property of some value. In the first case, we access the length property of the value in myString. In the second, we access the property named max in the math object, which is a collection of mathematics-related constants and functions. Almost all JavaScript values have properties. The exceptions are null and undefined. If you try to access a property on one of these non-values, you get an error. The 2 main ways to access properties in JavaScript are with a dot and with square brackets. Both value.x and value square brackets x access a property on value, but not necessarily the same property. The difference is how x is interpreted. When using a dot, the word after the dot is the literal name of the property. When using square brackets, the expression between the brackets is evaluated to get the property name. Whereas value.x fetches the property of value named x, value square brackets x takes the value of a variable named x and uses that converted to a string as the property name. If you know that the property in which you are interested is called color, you say value.color. If you want to extract the property named by the value held in the binding I, you say value square brackets I. Property names are strings. They can be any string, but the dot notation works only with names that look like valid binding names, starting with a letter or underscore and containing only letters, numbers, and underscores. If you want to access a property named 2 or John Doe, you must use square brackets, value square brackets 2 or value square brackets John Doe. The elements in an array are stored as the array's properties using numbers as property names. Because you can't use the dot notation with numbers and usually want to use a binding that holds the index anyway, you have to use the bracket notation to get at them. Just like strings, arrays have a length property that tells us how many elements the array has. Methods. Both string and array values contain, in addition to the length property, a number of properties that hold function values. Every string has a toUpperCase property. When called, it will return a copy of the string in which all letters have been converted to uppercase. There is also toLowerCase going the other way. Interestingly, even though the call to uppercase does not pass any arguments, the function somehow has access to the string do, the value whose property we called. You'll find out how this works in Chapter 6. Properties that contain functions are generally called methods of the value they belong to, as in toUpperCase is a method of a string. This example demonstrates two methods you can use to manipulate arrays. The push method adds values to the end of an array. The pop method does the opposite, removing the last value in the array and returning it. These somewhat silly names are the traditional terms for operations on a stack. A stack in programming is a data structure that allows you to push values onto it and pop them out again in the opposite order so that the thing was last added was removed first. Stacks are common in programming. You might remember the function callStack from the previous chapter, which is an instance of the same idea. Objects. Back to this weresquirrel. A set of daily log entries can be represented as an array, but the entries do not consist of just a number or a string. Each entry needs to store a list of activities and a Boolean value that indicate whether Jacques turned into a squirrel or not. Ideally, we would like to group these together in a single value and then put those grouped values into an array of log entries. Values of the type object are arbitrary collections of properties. One way to create an object is by using braces as an expression. Inside the braces, you write a list of properties separated by commas. Each property has a name followed by a colon and a value. When an object is written over multiple lines, indenting it as shown in this example helps with readability. Properties whose names aren't valid binding names or valid numbers must be quoted. This means that braces have two meanings in JavaScript. At the start of a statement, they begin a block of statements. In other position, they describe an object. Fortunately, it is rarely useful to start a statement with an object in braces, so the ambiguity between these two is not much of a problem. The one case where this does come up is when you want to return an object from a shorthand arrow function. You can't write n equals greater than prop n since the braces will be interpreted as a function body. Instead, you have to put a set of parentheses around the object to make it clear that it is an expression. Reading a property that doesn't exist will give you the value of undefined. It is possible to assign a value expression to the equals operator. This will replace the property's value if it's already existed or create a new property if the object if it didn't. To briefly return to our tentacle model of bindings, property bindings are similar. They grasp values, but other bindings and properties might be holding on to those same values. You can think of objects as octopuses with any number of tentacles, each of which has a name written on it. The delete operator cuts a tentacle off from an octopus. It is a unary operator that when applied to an object property will remove the named property from the object. This is not a common thing to do, but it is possible. The binary in operator, when applied to a string in an object, tells you whether that object has a property with that name. The difference between setting a property to undefined and actually deleting it is that in the first case, the object still has the property. It just doesn't have a very interesting value. Whereas in the second case, the property is no longer present and in will return false. To find out what properties an object has, you can use object.keys function. Give the function an object and it will return an array of strings, the object's property names. There's an object.assign function that copies all properties from one object to another. Arrays then are just a kind of object specialized in storing sequences of things. If you evaluate type of empty brackets, it produces object. You can visualize arrays as long, flat octopuses with all their tentacles in a neat row, labeled with numbers. Jacques will represent the journal that Jacques keeps as an array of objects. Mutability. We will get to actual programming soon, but first there's one more piece of theory to understand. We saw that object values can be modified. The types of values discussed in earlier chapters, such as numbers, strings, and booleans, are all immutable. It is impossible to change values of those types. You can combine them and derive new values from them, But when you take a specific string value, that value will always remain the same. The text inside it cannot be changed. If you have a string that contains cat, it is not possible for other code to change a character in your string to make it spell rat. Objects work differently. You can change their properties, causing a single object value to have different content at different times. When we have two numbers, 120 and 120, we can consider them precisely the same number whether or not they refer to the same physical bits. With objects, there's a difference between having two references to the same object and having two different objects that contain the same properties. Consider the following code. The object1 and object2 bindings grasp the same object, which is why changing object1 also changes the value of object2. They are said to have the same identity. The binding object3 points to a different object, which initially contains the same properties as object1, but lives a separate life. Bindings can also be interchangeable or constant, but this is separate from the way their bindings behave. Even though number values don't change, you can use a let binding to keep track of a changing number by changing the value at which the binding points. Similarly, through a const binding to an object can itself not be changed and will continue to point at the same object, the contents of that object might change. When you compare objects with JavaScript's double equals operator, it compares by identity. It will produce true only if both objects are precisely the same value. Comparing different objects will return false even though they have identical properties. There is no deep comparison operation built into JavaScript that compares objects by contents, but it is possible to write it yourself, which is one of the exercises at the end of the chapter. The lycanthrope's log. Jacques started up his JavaScript interpreter and sets up the environment he needs to keep his journal. Note that the object added to the journal looks a little odd. Instead of declaring event properties like events, it just gives property name events. This is shorthand that means the same thing. If a property name in brace notation isn't followed by a value, its value is taken from the binding with the same name. Every evening at 10 p.m., or sometimes the next morning after climbing down from the top shelf of his bookcase, Jacques records the day. Once he has enough data points, he intends to use statistics to find out which of these events may be related to the squirrelifications. Correlation is a measure of dependence between statistical variables. A statistical variable is not quite the same as a programming variable. In statistics, you typically have a set of measurements, and each variable is measured for every measurement. Correlation between variables is usually expressed as a value that ranges from -1 to 1. Zero correlation means the variables are not related. A correlation of 1 indicates that the two are perfectly related. If you know one, you also know the other. -1 also means that the variables are perfectly related but are opposites. When one is true, the other is false. To compute the measure of correlation between two Boolean variables, we can use a phi coefficient. This is a formula whose input is a frequency table containing the number of times the different combinations of the variables were observed. The output of the formula is a number between -1 and 1 that describes the correlation. We could take the event of eating pizza and put that in a frequency table like this, where each number indicates the number of times that combinations occurred in our measurement. If we call that table n, we can compute phi using the following formula. If at this point you're putting the book down to focus on a terrible flashback to the 10th grade math class, hold on. I did not intend to torture you with endless pages of cryptic notation. It is just this one formula for now, and even this one, all we need to do is turn it into JavaScript. The notation n to the 0, 1 indicates the number of measurements which the first variable, squirrelness, is false, 0, and the second variable, pizza, is true, 1. In the pizza table, n01 is 9. The value n1 refers to the sum of all measurements where the first variable is true, which is 5 in the example table. Likewise, n.0 refers to the sum of the measurements where the second variable is false. So, for the pizza table, the part above the division line, the dividend, would be 1 times 76 minus 4 times 9 equals 40. And now the part below it, the divisor, would be the square root of 5 times 85 times 10 times 80, or the square root of 340,000. This comes out to be phi roughly equal to 0.069, which is tiny. Eating pizza does not appear to have an influence on the transformations. Computing correlation. We can represent a 2x2 table in JavaScript with a 4-element array, 7, 9, 4, 1. We could also use other representations such as an array containing 2-element arrays, 76, 9, 4, 1, or an object with property names like 11 and 0, 1. But the flat array is simple and makes the expressions that access the table pleasantly short. We'll interpret the indices to the array as a 2-bit binary numbers, where the leftmost, most significant digit refers to the squirrel variable, and the rightmost, least significant digit refers to the event variable. For example, the binary number 10 refers to the case where Jacques did not turn into a squirrel, but the event, say pizza, didn't occur. This happened 4 times, and since binary 10 is 2 in decimal notation, we will store this number at index 2 of the array. This is the function that computes the phi coefficient from such an array. This is a direct translation of the phi formula into JavaScript. Math.squareroot is the square root function as provided by the math object in a standard JavaScript environment. We have to add 2 fields from the table to get fields like n1 because the sum of rows or columns are not stored directly in our data structure. Jacques keeps his journal for 3 months. The resulting dataset is available in the coding sandbox for this chapter, where it is stored in the journal binding and in downloadable file. To extract a 2x2 table for a specific event from the journal, we must loop over all the entries and tally how many times the events occur in relation to squirrel transformations. Arrays have an includes method that checks whether a given value exists in the array. The function uses that to determine whether the event name is interested in a part of the event list for a given day. The body of the loop in table 4 figures out of which the box in each table each journal entry falls into by checking whether the entry contains a specific event it's interested in or whether the event happens alongside a squirrel incident. The loop then adds 1 to the correct box in the table. We now have the tools we need to compute individual correlations. The only step remaining is to find a correlation for every type of event that was recorded and see whether anything stands out. Array loops. In the table 4 function, there's a loop like this. This kind of loop is common in classical JavaScript. Going over arrays one element at a time is something that comes up a lot. And to do that, you'd run a counter over a length of an array and pick out each element in turn. There's a simpler way to write such loops in modern JavaScript. When a for loop uses a word of after its variable definition, it will loop over the elements of the value given after of. This works not only for arrays, but also for strings and some other data structures. We'll discuss how it works in Chapter 6. The final analysis. We need to compute a correlation for every type of event that occurs in the dataset. To do that, we first need to find every type of event. By adding any event names that aren't already in the events array, the function collects every type of event. Using that function, we can see all the correlations. Most correlations seem to lie close to 0. Eating carrots, bread, or pudding apparently does not trigger squirrel lycanthropy. The transformations do seem to occur somewhat more often on weekends. Let's filter the results to show only correlations greater than 0.1 or less than negative 0.1. Aha! There are 2 factors with a correlation clearly stronger than the others. Eating peanuts has a strong positive effect on the chance of turning into a squirrel, whereas brushing teeth has a significant negative effect. Interesting, let's try something. That's a strong result. The phenomenon occurs precisely when Jacques eats peanuts and fails to brush his teeth. If only he weren't such a slob about dental hygiene, he'd never have even noticed his affliction. Knowing this, Jacques stops eating peanuts altogether and finds that his transformations stop. But it only takes a few months for him to notice that something is missing from this entirely human way of living. Without his feral adventures, Jacques hardly feels alive at all. He decides he'd rather be a full-time wild animal. After building a beautiful little treehouse in the forest and equipping it with a peanut butter dispenser and a 10-year supply of peanut butter, he changes form one last time and lives the short and energetic life of a squirrel. Further, arrayology. Before finishing the chapter, I want to introduce you to a few more object-related concepts. I'll start with some generally useful array methods. We saw push and pop, which add and remove elements at the end of an array, early in this chapter. The corresponding methods for adding and removing things at the start of an array are called unshift and shift. This program manages a queue of tasks. You add tasks to the end of the queue by calling remember groceries, and when you're ready to do something, you call getTask to get and remove the front item from the queue. The remember urgently function also adds a task, but it adds it to the front instead of the back of the queue. To search for a specific value, arrays provide an index of method. The method searches through the array from the start to the end and returns the index at which the requested value was found, or -1 if it wasn't found. To search from the end instead of the start, there's a similar method called last index of. Both index of and last index of take an optional second argument that indicates where to start searching. Another fundamental array method is slice, which takes start and end indices and returns an array that has only the elements between them. The start index is inclusive and the end index is exclusive. When the end index is not given, slice will take all of the elements after the start index. You can also omit the start index to copy the entire array. The concat method can be used to append arrays together to create a new array, similar to what the plus operator does for strings. The following example shows both concat and slice in action. It takes an array and an index and returns a new array that is a copy of the original array with the element at the given index removed. If you pass concat an argument that is not in an array, that value will be added to the new array as if it were a one-element array. Strings and their properties. We can read properties like length and to uppercase from string values, but if we try to add a new property, it doesn't stick. Values of type string, number, and boolean are not objects, and though the language doesn't complain if you try to set a new property on them, it doesn't actually store those properties. As mentioned earlier, such values are immutable and cannot be changed. But these types do have built-in properties. Every string value has a number of methods. Some very useful ones are slice and index of, which resemble the array methods of the same name. One difference is that a string's index of can search for a string containing more than one character, whereas the corresponding array method looks only for a single element. The trim method removes whitespace, spaces, new lines, tabs, and similar characters from the start and end of a string. The zeroPad function from the previous chapter also exists as a method. It is called padStart and takes the desired length and padding character as arguments. You can split a string on every occurrence of another string with split and join it again with join. A string can be repeated with the repeat method, which creates a new string containing multiple copies of the original string glued together. We have already seen the string type's length property. Accessing the individual characters in a string looks like accessing array elements, with a complication that we'll discuss in Chapter 5. Rest parameters. It can be useful for a function to accept any number of arguments. For example, math.max computes the maximum of all the arguments it is given. To write such a function, you put 3 dots before the function's last parameter like this. When such a function is called, the rest parameter is bound to an array containing all further arguments. If there are other parameters before it, their values aren't part of the array. When, as in max, it is the only parameter, it will hold all arguments. You can use a similar 3-dot notation to call a function with an array of arguments. This spreads out the array into the function call, passing its elements as separate arguments. It is possible to include an array like that along with other arguments such as max, 9, 3 dots, numbers, 2. Square bracket array notation similarly allows a triple dot operator to spread another array into the new array. This works even in curly brace objects where it adds all properties from another object. If a property is added multiple times, the last value to be added wins. The math object. As we've seen, math is a grab bag of number-related utility functions such as math.max, maximum, math.min, minimum, and math.squareroot, square root. The math object is used as a container to group a bunch of related functionality. There is only one math object, and it is almost never useful as a value. Rather, it provides a namespace so that all these functions and values do not have to be global bindings. Having too many global bindings pollutes the namespace. The more names have been taken, the more likely you are to accidentally overwrite the value of some existing binding. For example, it is not unlikely you'll want to name something max in one of your programs. Since JavaScript's built-in max function is tucked safely inside of the math object, you don't have to worry about overwriting it. Many languages will stop you, or at least warn you when you are defining a binding with the same name that is already taken. JavaScript does this for bindings you declared with let or const, but, perversely, not for standard bindings, nor for bindings declared with var or function. Back to the math object. If you need to do trigonometry, math can help. It contains cos, cosine, sine, sine, and tan, tangent, as well as their inverse functions, acos, asyn, and atan, respectively. The number pi, or at least the closest approximation that fits in a JavaScript number, is available as math.pi. There is an old programming tradition of writing the names of constant values in all caps. If you're not familiar with sines and cosines, don't worry, I'll explain them when they're used in Chapter 14. The previous example used math.random. This is a function that returns a new pseudo-random number between 0 inclusive and 1 exclusive every time you call it. Though computers are deterministic machines, they always react the same way if given the same input. It is impossible to have them produce numbers that appear random. To do that, the machine keeps some hidden value, and whenever you ask for a new random number, it performs complicated computations on this hidden value to create a new value. It stores a new value and returns some number derived from it. That way, it can produce ever new, hard to predict numbers in a way that seems random. If we want a whole random number instead of a fractional one, we can use math.floor, which rounds down to the nearest whole number on the result of math.random. Multiplying the random number by 10 gives us a number greater than or equal to 0 and below 10. Since math.floor rounds down, this expression will produce with equal chance any number from 0 to 9. There are also the functions math.ceil for ceiling, which rounds up to a whole number, math.round to the nearest whole number, and math.abs, which takes the absolute value of a number, meaning it negates negative values but leaves positive ones as they are. Destructuring. Let's return to the phi function for a moment. One reason this function is awkward to read is that we have a binding pointing at our array, but we much prefer to have the bindings for the elements of the array, that is, let n00 equals table 0 and so on. Fortunately, there's a succinct way to do this in JavaScript. This also works for bindings created with let, var, or const. If you know that the value you're binding is an array, you can use the square brackets to look inside of that value, binding its contents. A similar trick works for objects using braces instead of square brackets. Note that if you would try to destructure null or undefined, you get an error, much as you would if you directly try to access a property of those values. Optional property access. When you aren't sure whether a given value produces an object but still want to read a property from it when it does, you can use a variant of the dot notation, object?dot_property. The expression a?dot_b means the same as a.b when it isn't null or undefined. When it is, it evaluates to undefined. This can be convenient when, as in the example, you aren't sure that a given property exists or when a variable might hold an undefined value. A similar notation can be used as square bracket access, and even with function calls by putting $dot in front of the parentheses or brackets. JSON. Because properties grasp their value rather than contain it, objects and arrays are stored in a computer's memory as sequences of bits holding the addresses, the place in memory of their contents. An array with another array inside of it consists of at least one memory region for the inner array and another for the outer array, containing, among other things, a number that represents the address of the inner array. If you want to save data in a file for later or send it to another computer over the network, you have to somehow convert these tangles of memory addresses to a description that can be stored and sent. You could send over your entire computer memory along with the address of the value you're interested in, I suppose, but that doesn't seem like the best approach. What we can do is serialize the data. That means it's converted to a flat description. A popular serialization format is called JSON, pronounced JSON, which stands for JavaScript Object Notation. It is widely used as a data storage and communication format on the web, even with languages other than JavaScript. JSON looks similar to JavaScript's way of writing arrays and objects, with a few restrictions. All property names have to be surrounded by double quotes, and only simple data expressions are allowed. No function calls, bindings, or anything that involves actual computation. Comments are not allowed in JSON. A journal entry might look like this when represented as JSON data. JavaScript gives us the functions json.stringify and json.parse to convert data to and from this format. The first takes a JavaScript value and returns a JSON encoded string. The second takes such a string and converts it to the value it encodes. Summary. Objects and arrays provide ways to group several values into a single value. This allows us to put a bunch of related things in a bag and run around with the bag instead of wrapping our arms around all of the individual things and trying to hold on to them separately. Most values in JavaScript have properties, with the exceptions being null and undefined. Properties are accessed using value.prop or valueprop. Objects tend to use names for their properties and store more or less a fixed set of them. Arrays, on the other hand, usually contain varying amounts of conceptually identical values and use numbers starting from 0 as the names of their properties. There are some named properties in arrays, such as length and a number of methods. Methods are functions that live in properties and usually act on the value of which they are a property. You can iterate over arrays using a special kind of for loop, for let element of array. Exercises. The sum of a range. The introduction of this book alluded to the following as a nice way to compute the sum of a range of numbers. Write a range function that takes two arguments, start and end, and returns an array containing all the numbers from start up to and including end. Next, write a sum function that takes an array of numbers and returns the sum of these numbers. Run the example program and see whether it does indeed return 55. As a bonus assignment, modify your range function to take an optional third argument that indicates the step value used when building the array. If no step is given, the element should go up by increments of 1, corresponding to the old behavior. The function call range 110.2 should return 13579. Make sure this also works with negative step values so that range 5 to negative 1 produces 5432. Reversing an array. Arrays have a reverse method that changes the array by inverting the order in which its elements appear. For this exercise, write two functions, reverse array and reverse array in place. The first, reverse array, should take an array as its argument and produce a new array that has the same elements in the inverse order. The second, reverse array in place, should do what the reverse method does, modify the array given as its argument by reversing its elements. Neither may use the standard reverse method. Thinking back to the notes about side effects and pure functions in the previous chapter, which variant do you expect to be useful in more situations? Which one runs faster? A list. As generic blobs of values, objects can be used to build all sorts of data structures. A common data structure is a list, not to be confused with arrays. A list is a nested set of objects with the first object holding a reference to the second and the second to the third, and so on. The resulting objects form a chain as shown in the following diagram. A nice thing about lists is they can share parts of their structure. For example, if I create two new values, value 0 rest list and value -1 rest list, with a list referring to the binding defined earlier, they are both independent lists, but they share the structure that makes up their last three elements. The original list is also a valid three-element list. Write a function array2list that builds up a list structure like the one shown when given 1, 2, 3 as argument. Also write a list2array function that produces an array from the list. Add the helper function prepend, which takes an element and a list and creates a new list that adds the element to the front of the input list, and nth, which takes the list and a number and returns the element at the given position of the list, with 0 referring to the first element or undefined when there is no such element. If you haven't already, also write a recursive version of nth. Deep comparison. The equals operator compares objects by identity, but sometimes you prefer to compare the values of their actual properties. Write a function deep equal that takes two values and returns true only if they are the same value and are objects with the same properties, where the values of the properties are equal when compared with the recursive call to deep equal. To find out whether values should be compared directly using the triple equals operator for that, we have their properties compared. You can use the type of operator. If it produces objects for both values, you should do a deep comparison. But if you have to take one silly exception into account because of a historical incident, type of null also produces object. The object.keys function will be useful when you need to go over the properties of objects to compare them.